Okay, I think we'll get started. Today we're going to learn about capacitors, and you can likely do this at home. We're going to try to make this capacitor out of aluminum foil and see if we can get some of the ideas associated with capacitors to come out in our hands-on experiment here. Okay, so a basic parallel plate capacitor consists, just as the name implies, of two metal plates. In our case, we're going to be using aluminum foil, so hopefully you have some of that at home. And if you could just cut two pieces that look like this. The square part of this is going to be the capacitor part, and this is going to be a lead. This is going to be where we hook up our leads. So the sheet I have, I just took two sheets of aluminum foil and then cut them, stuck them together and cut them, and now I have two separate sheets. Here's one of the sheets, and so you could do that with your own aluminum foil. Now, once we have the two sheets, the role of a capacitor is to store charge, and so if we were to hook this up to a battery, which we're not going to do, we're actually going to just measure, at first anyway, just measure the capacitance directly with the multimeter. But if we were to hook this up with a battery, we would start to develop some amount of charge on these plates. Now, the amount of charge that can be stored is based on, one, the voltage of the battery. So what's going to happen is you'll get an electron coming out of this end of the battery, and because this is all connected with a wire, that's free to move over to this plate, and we'll have an electron head back to the positive terminal of the battery. This will build up an excess of electrons on the bottom and an excess of positive charge on the top. Now, eventually, we'll have a separation of charge here that creates a voltage difference across this capacitor, and that's going to continue to strip charge from here, strip electrons from here, add electrons from here, until the voltage difference equals the battery. So if we have a stronger battery, we're going to be able to get a larger voltage difference. Now, how much charge we can store, Q, is going to depend on that voltage. So we would expect it to depend on the voltage, but it will also depend on the characteristics of these plates. For example, if the charge can spread out more, if the charge can be, we don't want to, as we pack more and more electrons here, they want to repel each other. So if we can spread that charge out more, if we can stabilize this by getting these two plates closer together, then we will be able to store more charge. That characteristic is called capacitance, and we have the letter C here for that. So let's just talk about intuitively what's going to happen. If I have a certain amount of area here on this plate, so I showed you that aluminum plate, if that's bigger, the same amount of charge can spread out more, which makes it a little more stable, and so the capacitance will go up. So we would expect, as we increase the area, we should increase the capacitance. Likewise, if we decrease this distance, it might be a little counterintuitive at first, but let's think about this. If we decrease the distance, then these charges are going to feel each other more, right? And since it's positive and negative, that's going to be an attractive force, and that's going to stabilize. It's going to allow for more electrons to fill up here and more positive charge over here. So as the distance goes down, then as the distance goes up, the capacitance goes down, and vice versa. As the distance goes down, the capacitance goes up. So there's an inverse relationship with distance. Then finally, and we've got we've got three epsilons here running around. We've got the battery electromotive force. We have permittivity of free space, which is just a constant of nature, and then we're going to have what's called the dielectric constant. So we could put something in here in between these charges rather than just air, and air is pretty close to a vacuum. So if you have just air in between, then those charges really feel each other completely. If you put something in between, a dielectric as it's called, that material will respond to those forces in a way that mitigates the effect of each of these feeling each other. So that stabilizes the capacitance. So as we place a dielectric in between, then we can enhance the capacitance. So this will polarize and allow for stability of these charges here and here. And so as the dielectric constant will go up, if we were to stick something with a high dielectric constant in between those plates, will increase our capacitance. So overall, our capacitance is linear. This is not necessarily intuitive. Why is it linear? But it is linear in area, and it is linear in dielectric constant, and then it is inversely related to the first power of the distance between the plates. And then the constant of proportionality here is this permittivity of free space. So that's just a constant of nature. And so this is the formula we're going to be exploring today. So we're going to be varying the distance. We're going to be varying the area. We will vary we can vary the dielectric constant, although we don't have a lot of control over that. We're going to use pieces of paper as our dielectric constant, or saran wrap, something like that. And those are very similar in dielectric constant. So we won't see a big difference. Okay, so should have some aluminum foil, some kind of copier paper. That would be enough. If you want to try some saran wrap or plastic wrap or some wax paper. I've also got a sheet of Teflon. But again, the dielectric constants here are all somewhere around 2 to maybe 3 in here. So we're not going to see a good variability there. Here's where you might be lacking at home, hopefully not, but if so, you can just follow along. Ideally, if you have a multimeter with the ability to measure capacitance, that's what we're going to do first. And so we're just going to directly measure capacitance. And in fact, after that's done, if you want to just stop and say, hey, that's enough for me, then that's good. We're going to go into some electronics afterwards, and we're going to convert that capacitance first convert it to a sequence of pulses, so a frequency, and we're going to measure that on the oscilloscope. So we're going to use something called a 555 timer to convert the capacitance to frequency, and then we'll measure that on the scope. And finally, we will use what we built here, and we'll send it into another IC, the 74HC4046, which will allow us to convert frequency into voltage. Then we could measure that with a regular voltmeter. So if you have a voltmeter but doesn't have the capacitance capability, that's something that you could do there. If you also don't have a scope, oscilloscope. And then finally, I won't say too much about this, but we could feed that into a microcontroller, for example, that has a LED screen, and you could just display this. So we'll kind of quickly do this at the end. But for now, let's get started with setting this up and reading the capacitance on the multimeter and gathering some data. Okay, so here's our setup. And first thing is you'll want to get the area of your sheet of aluminum. So this happens to be 24 centimeters by 19.3 roughly. So that works out to be this area in square meters. And then I've got the permittivity of free space here, and that's again a constant of nature, and then our formula that we're going after. This is just information for me. I just recorded a quick measurement, but we'll be more careful here now. So what we're going to do first is we are going to take and place 10 sheets of paper, just copy paper, in between. And then what we're going to try to do is, by eye, best we can, line up these two sheets so that they're on top of each other. And then I've got leads connected to the aluminum foil. Tried to solder them there, but it doesn't solder very well. So I've got leads here, and then they are going to the multimeter. So I'm going to turn this around like this, so that hopefully when I turn on the multimeter, okay, so that's a little better there. All right, so we are measuring 0.2 nanofarads, but notice the trouble with the aluminum foil is that it doesn't lie flat. So let's go ahead, and I'm going to place some books on, and what we're going to do is notice a couple of things. So I'm going to place this book on. This is 1 kilogram, and notice if I press down, we get a difference in capacitance, and that's because it's pushing out or squeezing those two plates together. There's a little flex in there, and in fact there's quite a bit of flex in there. So this is going to be one issue that we're going to have, is that we won't be able to come to a consistent we won't be able to come with any kind of reasonable weight to a point where this stops, but we'll just add some weight, and then we'll add the same weight each time. So this book is 2.3 kilograms, so we're at 3.3 kilograms, and now I'm going to add a 10 kilogram weight on top of that. And so that is what we're reading here now with 10 sheets of paper. So what we're going to do is we're going to record this, and then we're going to remove that sheet of paper. So let me go to now where we've got some Google Sheets here, and I've just filled these in with numbers. So let's go in and fill these in. So this is with 10 sheets of paper, and we're measuring 1.03 nanofarads. So I'll just do, I'll take out one sheet and then another sheet and another sheet, and I don't think you will need to watch me do that. I'll do the first one, and then I'll pause the video, and we can you can, if you're doing this at home, you can go ahead and fill out your 10 sheets. Otherwise, you can just see what data come out when we do this. So I'm going to remove the weight. So that one of the tricks here will be consistency. So I'm going to pull out one sheet of paper. And then important to get these lined up as best we can. So now we're getting, looks like 1.11. And I will pause the video here now and fill out the rest of these data. Okay, so finish this last one, and we've got a nice decaying curve here. So looks like 1 over. Notice I've got this, I shouldn't actually have the trend line in, because we don't expect this to be linear. We expect it to be 1 over. So what I'll do now is let's make an additional graph by plotting 1 over the distance in units of sheets of paper. And so we'll go capacitance versus 1 over the distance. So I will pause the video now, and so we'll just go 1 over number of sheets of paper versus capacitance, and we'll see if it's somewhat linear. Now, it might not be exactly linear. You can kind of make a prediction here. If it's not, we can kind of understand that there's that flex, and when you have more sheets of paper, you might get more flex than if you have a smaller sheet of paper. So that could introduce some nonlinearity in these units of measurement of sheets of paper. So I will pause the video here. I will take and change this column here now to 1/, sheets of paper. Okay, so now I have taken sheets to the -1, and notice by eye it looks fairly linear, but when you put a line in, there is a little bit of a curve. So that's kind of what I expected, that there should be a bit of nonlinearity in here just because of that flex to the paper. And even you can see here, as this has been sitting here, it's been kind of compressing a little bit, a small amount. So 5.82 was my last measurement, and now that it's been sitting for some time, it's 5.91. So each one of these would flex a little differently, but we can by and large see that this is linear, and so good demonstration of the behavior with distance. Okay, so now let's do area, and so let's take a look at our sheet here. Oh, I can take that measurement, 5.91. So I will put that here. And then what we will do is try as best we can by eye to move our paper, our sheets, so they're not completely overlapping. So now we're going to only overlap 75% of the sheet. And we'll give it maybe a little bit of time to, actually I'll give it a little press down and then come back. We'll call it 4.92. And I will pause the video now and get the other two measurements. Okay, so now we're back, and got this fraction of the area and then the capacitance in nanofarads. So again, we see fairly linear response here, as we would expect. All right, so that's the two characteristics, the area and the distance. You could try putting something besides paper in to get a sense of the dielectric constant. Unfortunately, as I mentioned on the whiteboard, most of these dielectric constants are pretty close to one another. So you'll notice some difference, but not a significant difference. Okay, so now what we're going to do is instead of making a direct measurement of the capacitance, in this case in nanofarads, with our voltmeter, let's do a couple of things. The next thing we're going to do here now is create a circuit that will convert capacitance to a frequency. Okay, so let's look at this 555 timer capacitance to frequency circuit that we're going to build here. 555 timer, of course, a very important IC, and it's used in all sorts of things for producing, well, one aspect it's used is for producing regular clock cycles. And so the basic setup is here. It's an 8-pin chip, and the schematic that we're going to use is a relatively simple setup. It's in the so-called astable configuration, and what we're going to do is our capacitor is going to be right here, and that's going to influence the frequency at which the output signal comes out. So this schematic here, these pin numbers correspond to these pin numbers, and we'll go to the board now in the breadboard itself. So let's go take a look at that. Okay, so here we are, kind of a zoom in. This is the top side of the chip. It's hard to see. There's a little, the cutout is up here. We have the various setup that we had on the board there. Key points here are this wire and this brown wire are coming from our capacitor, from our aluminum foil capacitor. So this brown wire is one of the leads is going to ground, and then this is going to input the trigger pin. This is the 100K, this is the 4.7K, this is the 10 nanofarad capacitor. These leads are going to the oscilloscope, and so we're going from the output pin number 3, and ground to our oscilloscope. And so this is our general setup. I'm going to back this up now, this camera up, and so that we can see our capacitor again. Now, backing out, we have a couple of pins here, this orange pin and this green pin. This is going to be going to our next circuit, which we'll put on delay there. But what I will be doing is off camera, I'm going to be recording a voltage that we will need in the next section. So while I'll be recording these, we won't be talking about this quite yet. So let me switch here now to the scope, and again I apologize for the blurriness. This is the best this camera can do. I will be able to point out, I'll just report the values here. They don't show up quite well enough. That's right now it's at 5.48 kilohertz. Notice now when I press down on the capacitor, changing the capacitance, we get a change in the frequency. So let me load this up with our normal weight, and I've just left this sitting at the 1/4 level, so we can go and record that. Okay, so I'm seeing 3.49 as our kilohertz. So I'm going to switch here now to frequency, and we're here. So what did I say there? 3.48, and this will be kilohertz. And then I will measure a voltage here as well, which we'll talk about later. What we're going to be doing is trying to do a frequency to voltage conversion so that we can read this in with the analog to digital on a microcontroller, or just on our multimeter if our multimeter does not have a capacitance measurement. The voltage reading here is 1.436. All right. I'm going to go back to our oscilloscope, and now we are going to move back to half. And we're getting 1.9 kilohertz. So and 1.257. That's our voltage. Notice the way this is set up, the frequency goes down as the capacitance goes up. So it's inversely, the frequency coming out of the 555 timer is inversely proportional to the capacitance. So I'm going to pause the video now and get the remaining two measurements, and that will give us a way to calibrate then the capacitance that we measured directly with the frequency and with the voltage. Okay, so I finished recording those data and plotted 1 over frequency versus 1 over capacitance, relatively linear here. So we get a calibration function or calibration curve for that. And then we have voltage versus capacitance, relatively linear directly. And so we get a calibration curve for that. So these are our two calibration curves. And so this allows us to convert frequency into capacitance then. So if we want to use our oscilloscope, rather than having if our voltmeter doesn't have a capacitance measurement, we can measure the capacitance via the oscilloscope. Now, how we were able to do the calibration, because we directly measured the capacitance with the multimeter. What you would need to do if you don't have a multimeter is you would need to use a series of capacitors and known capacitors and get the frequency of known capacitors and then compare that to the frequency of your homemade capacitor. Okay, so that discusses the 555 timer circuit and how it can be used to convert the capacitance to frequency. Now, I've been keeping track of this voltage, and this will allow us then to use a voltmeter to convert to capacitance. So we can see here we could use this equation in this case. And again, you would need to use a set of capacitors if we weren't able to measure ours directly. But we could get a calibration curve here. So what we need to talk about yet is the circuit that will that produces this voltage, and then we'll just quickly feed that voltage into a multimeter, but also, well, we could probably skip that, but into a microcontroller. So let's go to the whiteboard again and look at the circuit for the chip called the 74HC4046. Okay, so the 74HC4046 is a phase lock loop chip, and there are good videos on YouTube to talk about how all the phase lock loop works and how this chip works. So I won't go into that in any kind of detail here. Just to set up what is going on in terms of our signal. So we have coming in, we've already seen now we can convert our capacitance to frequency from the 555 timer. So the 555 timer is going to be sending in the signal, and I went through those wires there when we were looking at them. So that will come into our signal pin, and then what happens is this chip will try as best as it can to lock in on the frequency and the phase, and it does so by adjusting the voltage control oscillator. So basically this chip has a voltage controlled oscillator, so it changes the voltage, changes the frequency, and it will adjust that voltage until it matches the frequency and the phase of the incoming signal, and it produces a phase lock signal coming out. My drawing is terrible here. These should be identical signal now coming out of the chip. This is not what we need, because we already have this really, so we know what it is converted to frequency, but we can kind of pull out additional information on based on how this chip works. So when you want to go into the phase lock loop setup, you need to have an external setup of a simple low pass filter. So just an RC filter. Here I'm using a 10K resistor and a 1 microfarad capacitor. So this phase comparator 2 setup, that's what's trying to get these phases connected, will output a signal, and if you run this through a low pass filter, then the voltage will settle in on something between VCC and ground that is precisely the right voltage to match the frequency. So essentially we've got a frequency to voltage converter, and since we had already converted our capacitance to frequency, then we have our capacitance to voltage converter. And so those were the data that we were taking earlier, the voltage. And where were we measuring that? That was coming out of this low pass filter. So that's the setup. And so basically we're kind of using this phase lock loop in a way that you wouldn't normally use it, but it's a way to get that voltage. So let's do that. And the reason we want that voltage is so that we can send this into either a voltmeter if our voltmeter can't read capacitance, or into a microcontroller. All right, so let's go to the board here. And again, this will be somewhat of a mess. Here's our chip here, and what we can see, the top side is up on this end here, and the bottom end down here. I'm not going to go through too much. These are the various resistors that were used in the setup from the whiteboard. And what we will see here, though, this green wire, this is what's coming from our 555 timer going to ground, so that matches the ground. And then the orange wire is coming from our 555 timer into the signal input pin here. Our low voltage or low frequency filter consists of this resistor and this capacitor. These two resistors, those go on R1 and R2, and those are used to adjust the range of the frequencies that this can operate at. And so I just kind of by trial and error using a 10K and a 10K for R1 and a 1 megohm for R2. This is our output, and this could go right into, this blue wire here could go right into a voltmeter. We're going to set it up to run into a microcontroller, and the particular microcontroller we're using is called a LuckFox Pico. You could use a Raspberry Pi Pico, that'd probably be an easier one to use. I've just been using a lot of I've been doing a series on the LuckFox, so I've been using that a lot. The trouble with the LuckFox is its analog to digital converter is limited to a total voltage of 1.8 volts. So we saw, I have a voltage divider here to make sure that we don't exceed 1.8 volts. And we saw in our data that we collected that we were within that range. All right, so this is the setup here for this chip. So what we'll do now is we will switch over to looking at the voltage going into a meter and into the LuckFox. Okay, so now the final part. We've got our voltage coming out of our phase lock loop, our 74HC4446, and we can then feed that in along with our calibration curve to get the capacitance that we would measure on our voltmeter. And so we're feeding this into in this case, a LuckFox Pico Max, which is what I've been using lately, but Raspberry Pi Pico would be perfect for this. This is connected to an OLED, and so the voltage comes in the analog to digital port right here on the LuckFox, and then through I2C communication with the OLED, the calibration curve is applied. Then we'll output the raw voltage that's coming in, and we will also get the capacitance. So notice if I'll press down on the capacitor and we get a change. So it's reading live and responsive. I'm going to back this camera out. Here's our capacitor here, kind of off screen a bit. But let me put the weight on. And so we're in the 4 nanofarad range. Maybe not exactly what we would get from the meter, but we didn't have a perfect calibration. And of course, the nature of this aluminum foil is such that it has that flex to it. But certainly in the right ballpark here. I'm going to try to zoom in on this a little bit. 4.03, 4.17 for the capacitance here. So this completes our application, or our lab here, with the building our own capacitor with aluminum foil.